Hello and welcome to my 10th lecture on operating system development. And today I wanted to conclude this topic of input and output devices. So previously I talked a bit about, peripheral devices and stuff, and we've been sort of building up to this. And generally, I would like for this video to be the final one about like input and output devices, so that we can move on to more interesting topics such as memory management or process scheduling, and I think those will be way more exciting. And that's because there's not really much that I can say about input and output devices. They're not like really a cool thing to talk about, in the sense that sure, they're like very nice to implement, and they can, it's lots of fun to actually play around with what we can do. But the thing is, all of those implementations and such, they don't have any cool ideas, per se. As in, it boils down to reading a manual or reading the official documentation of a given extension card or peripheral device, and you simply write a driver according to that manual or documentation. And obviously I'm not going to stand around here and say, oh, if you want to write a driver for this and this USB controller, you would write to this port and get to this base address and write to this buffer and this, because that would be tedious. So I talked about the most ubiquitous, let's say, devices in my previous video. If it comes to input, and that was the mouse and the keyboard, and I talked about that in detail. And today I want to talk in detail about basic graphical and audio output, and how I could further develop this, and I'll also superficially talk about USB, and then generally summarize the topic of I/O devices and extension cards in the context of an operating system. Okay, great. So, during my previous lecture, I drew a relatively nice diagram which demonstrated the general working idea of video graphics and how they're handled on a modern computing system. And basically you have a video card, right? Which nowadays is simply a subcomponent of a graphics card, where a graphics card is this huge thing which has a lot of computing power. It has those small parallel computing units which are able to process a lot of information and do operations related to linear algebra, such as matrix multiplication, which appear a lot in graphics programming. But because of their computational abilities, graphics cards are also pretty much abused outside of their general exploitation field in order to do other computations where linear algebra is used, for example, in machine learning. So we have this video card, which was the actual thing that is directly connected to your some sort of monitor, or, well, it doesn't have to be a monitor. It's any sort of display. Okay? So you have this display, and you obviously have some video interface through which your display and your video card are connected. So I think that the ones I mentioned in my previous video were like DisplayPort, HDMI, or like VGA. High definition media interface, or a video graphics array. And the thing is, those are obviously fascinating, and you can study like how those signals are sent in order to display anything you want on a display, and how modes work, and how you actually send information that corresponds to individual pixels coloring. So the task of making a video card is pretty cool, but it's not what concerns us as operating system developers. The video card actually handles all of the direct, setting the mode and then sending information to the mode. All of that is actually handled by the video card. So the only thing we need is some sort of way to actually interact with the video card. So obviously you have your random access memory, and I talked about memory mapped I/O, where in your random access memory you have something called a buffer. And this buffer stores information in a specific format for how a given peripheral thing should be done. So we have our CPU, which actually executes some instructions. And the fundamental idea that we've already seen with the VGA text mode is we have this buffer in the RAM, and it stores, it begins at for the default text mode, it starts at the hexadecimal address B8000, and then all the even bytes correspond to have an ASCII code, and all the odd addresses contain color information for that cell. So basically, the video card, it starts interpreting this buffer. It always interprets this buffer. It looks at the buffer, and whenever it tries to write to the screen, what it does is it looks at the buffer. It sees, okay, there's an even byte and there's this number. Let's see what character this corresponds to on the ASCII table. Grabs a font and then sends it to the display according to its functioning mechanism. And then it takes a look at the next one. It would probably have to take a look at two simultaneously, 2 bytes, and decide what color is that and what character is that, and then send it, right? And it would do it for, the whole buffer. So that's a fundamental idea. So whenever you want text to be displayed on the screen, you don't actually have to care about the specifics of how you could display text on some sort of display. The only thing you need is the CPU will write to a RAM, and you may write different things to the buffer. Like, for example, if you write the character age to the address B8000 and you're in the VGA 80x25 text mode, then the video card will take this information from the RAM either through something called a DMA channel or direct memory access, or it will have to communicate with the CPU in order to get access to the random access memory. The exact method is irrelevant here. What matters is that it takes this information from the RAM, it interprets it according to its documentation, and then it knows how to generate those electric signals that correspond to the image that we want. So that's the fundamental working idea of computer graphics. So I've mentioned the VGA text mode, and that it has this simple linear buffer where you have this, and you place a character there, then you place a color to position 1, then at the position 2 you place another character, and so on. But we might want to render graphics, and for that we would need different pieces of information to actually put in the buffer, and we also have to notify the video card, hey, you need to interpret the values that are in the buffer differently. and those are video modes. So the CPU actually has to inform a video card that it wants to change the video mode. And the video card, once it's communicated with, it can change the VGA mode, and that means that it will start sending the values to the display differently according to a given buffer. And once a given video mode is set, you may write to the buffer according to the specific format, and then it will take this data and transform it and send it to the display. So, how will we actually communicate with the video card? Well, in something like 64-bit long mode, you could always communicate through something like I/O ports. But that's actually not recommended, very much not recommended. And if you're dealing with the legacy BIOS, which is what I mentioned this video series focuses on, then you actually want the bootloader to already set a video mode. And this is because in real mode, it is very easy to just call a couple BIOS interrupts in order to instruct the video card to be set to a given mode. And then, once you've set it to that mode, it is very easy from even 64-bit long mode, so it just writes to the buffer in order to instruct what exactly should be presented on the display. Okay, awesome. So if you're writing your own bootloader, you'll simply have to add some additional lines that set the video mode that you desire. And if you're already using your bootloader, you have to check it as documentation. What can you do in order to set a given video mode and then obtain its linear frame buffer base address? So where does this actual buffer that you're supposed to write video data to, where does it actually begin in memory? So, for example, if you're using something like Grub, it has this whole multi-bit thing. You can tell it precisely what video mode you want, and then the multi-boot protocol will inform you back what is this frame buffer address. If you're using Lamine or something like that, I'm pretty sure Lamine actually has this, in its sample program, it's like minimalist. It already hands you over the base address of the linear frame buffer, so you already have that. That's very cool. And I think it even draws a little line of that to give you a demo of how to use the linear frame buffer. So that's how you deal with that on a legacy BIOS. Now, if you're using UEFI, there's actually something, well, the bootloader still usually does all of the setting, but it does it in a completely different way. It does it for something called GOP, the Graphics Output Protocol. And this is a very easy to manage abstracted away protocol for handling graphics, and you can use it in order to get a linear frame buffer base address on UEFI. But yeah, I'll be focusing on the legacy BIOS, and first I'll talk about video modes that are generally chosen, the sort of philosophy that was in older video modes, and how things have changed today. So it's important to mention that originally you only had a few video modes, and basically you would have to hope that both your video card and your display sort of, knows those modes, but since there was such a little amount of them and they were also standardized, you could usually safely assume that. And pretty much if it comes to graphics modes, there were two main modes that were highly popular. and you'll probably recognize both of them. Well, one of them is 320 by 200 pixels with an 8-bit color palette, which means that each one of those pixels could be one of the 256 colors from the VGA palette. And you also may modify the VGA palette as you wish. This is called the 13H mode, hexadecimal 13. It's widely known primarily for its appearance in all the DOS games, right? So when you had DOS games, those were written in 16-bit real-mode assembly, and you would use those same BIOS interrupts in order to set a video mode, and whenever someone wanted to make an actual graphical video game, it would usually operate on this resolution, which is 320 by 200, and it would use a 256 color palette. So this standard mode has a regular frame buffer base address, just like the text mode had B8000, V80 by 25 characters one. This mode has its base address of the frame buffer at this address, A0000. So the working principle would be very simple. Each and next address, each and every next byte in the frame buffer would just correspond to the next pixel on the screen. It's as simple as that. So you would have some sort of color palette, right? And let's say you had some color like 39, and let's arbitrarily assume that it would be blue. So you would set the value at this address to 39, and in this mode, right, the video card would take a look at this buffer, it would see this, and it would know, aha, I have to send such information to my display, such that the very first pixel, or the one in the left upper corner, would be the number, would be the color blue, right? And then the very next pixel, let's say arbitrarily 45 would be purple. So if you set that to 45, then it would know that the first pixel has to be blue and the second one has to be purple. Very simple. If you want to place a pixel of a given color at a given position XY, it's going to be, the formula is going to be pretty much the same for every linear frame buffer, except we will have to take into account something called bits per pixel. But for now, we will assume that we have 1 byte per pixel, like here. So to write to a given position XY, that would obviously be where our base address, where are we going to start? And then our y coordinate times how much one row is going to be, so 320 for our example, and then plus x. I think it's very obvious where you would get this formula from. So yeah, I think it's relatively trivial. So that's the general way you would interact with this mode, 13H. And another popular VGA mode used to be 640 by 480. And this was the 12H mode. So the 12H mode was a bit more, well, it had a higher resolution, but the reason why 13H mode was actually, I think, more popular than this mode is because this had a very strict limitation of only allowing a 16 color palette. So you only had 4 bits for color, right? Furthermore, another limitation which makes this a bit less accessible is that this mode actually does not use a linear frame buffer. So linear frame buffers are nice to deal with, right? We have some place and it corresponds to like a pixel or a character. The next place corresponds to a pixel or a character or maybe a color, and they're placed next to each other in a line. Very simple, which is why it's called a linear frame buffer. Very simple. But this actually uses, this is actually a planar mode, and you have to switch between pages and do some weird shit, and I'm honestly not a big fan of that. So these two facts, the fact that it has a very limited color palette and the fact that it's more difficult to deal with because it doesn't use a linear frame buffer, makes this a mode that is often chosen less, but it's still really popular, and people may recognize it, for example, from Temple OS, right? Temple OS is a relatively popular operating system which used this resolution. So, people thought back in the day that you would basically get like higher resolution displays, and displays would evolve and you would get higher resolutions, and what we would simply do is we would add those new names for all of those video modes. Like here we have this name 12H or 13H, right? We would simply make new IDs for every single mode that exists, right? But that approach didn't really work, and because of that, at a certain point, there had to be changes, and there had to be like a unified way to actually handle video modes such that every video card and every monitor actually has different video modes, and you can check for compatibility, you can check which modes are offered, and select one algorithmically that suits you best. And the IDs would be different on each and every computer. And that's why VESA, or the Video Electronics Standard Association, started working on a completely different way of actually setting and managing video modes. But they wanted to keep the simplicity of how modes were managed back in the classical VGA times. So back in classic VGA times, right, you would generally use the BIOS interrupt hexadecimal 10. And this is obviously, if you remember, I once said that, I think I gave this example in one of my early lectures for printing out a character. But this is actually a general interrupt that is used for video and graphics, right? So we have this interrupt, or rather interrupt vector of instructions, related to video. And in order to set a given mode, and this is most relevant to us, you would use the instruction with the AH register equal to 0. I will write that hexadecimal explicitly. And then AL would be the mode that you want to set. So for example, you could say 13H, and then you would be in the 520 by 200 mode, and then you could write to the linear frame buffer, which has its address at 0x A0000, right? Simple instruction, simple parameter, and then you just call the interrupt, and you get to set a video mode. Now, this was very comfortable. This was a very nice and, I may even say, elegant sort of way. Though this might be too strong of a word, but it's at least a simple, nice way of actually dealing with this. It's definitely not problematic. And they wanted to keep this simplicity. So they introduced something called VBE, which are VESA BIOS extensions. So the idea is you could have a motherboard where your BIOS is something called VBE or VESA BIOS extensions, and those would extend, highly extend, the abilities of the interrupt vector number hexadecimal 10, so the video interrupt vector. And the way that VBE works, we're currently at like version VBE, like 3.0, I think. You know, version obviously 1, then version 2 and version 3. And you have pretty much 3 instructions that really matter. One of them is VBE info, so this will grant you general information about VBE. And this actually corresponds to AX, because here the entire A register is actually going to dictate the instruction. Or, well, to be precise, all of the... When they extended the interrupt vector, what they did is they said, whenever you have AH, right, because this AH would always correspond to the instruction number. So they said, okay, for our VESA BIOS extensions, we're always going to make this 4F. But the problem was that, there wasn't a problem. This was a solution. They said, okay, this is going to be our VESA BIOS extensions instruction, but the precise instruction is actually going to be given by AL. But a simpler interpretation is simply to say that AX corresponds to the instruction. So AX equal to 4. I'm going to write it like this: AX 4F00. That's VBE info. So if you set the X register to that, obviously hexadecimal, and then you call the interrupt vector 10, hexadecimal 10, then you'll get back VBE info, and it will be stored according to a specific format. You can easily check the format in the official VBE documentation. In fact, they have pretty much ready assembly for you to just copy over that has the format of the entire thing. And well, DI is obviously going to be the address at which you want to store the VBE info. So you set AX to this, you set the DI to the address where you have, the entire thing pretty much copy-pasted from the documentation of which parameter is where, and you call the interrupt, and those are going to be filled by VBE. And there's pretty much, well, at least in my opinion, there's only really one important piece of information. I'm pretty sure the VESA signature is also there, so it might be good. So you can use this to verify if VESA BIOS extensions even exist by checking the VESA signature, whether this actually returns the VESA signature somewhere. But I think a very important field is something called the video mode pointer. Because it actually has the ID of the first video mode that is supported by the video card and the display. And this is extremely vital, because what you can do is you can test for different video modes, because as I said, at a certain point they decided that IDs will be non-consistent. They made static IDs like 13H and 12H up to a mode, well, because VESA BIOS extensions, you know, they still made some standard IDs, but only up to a resolution of 1280 by 1024 with 24-bit color, which is very good. I mean, 24-bit color is basically like modern, right? Because I mean, sometimes you might hear that we use 32-bit colors and color spaces, but that's only because we use ARGB, which has an additional byte for something called the alpha channel, which basically corresponds to the opacity of a color. It represents transparency and stuff, so that's what the alpha channel corresponds to. But the pure red, green, and blue, they usually, even like all modern things, they usually get a byte, right? So a 24-bit RGB is pretty good, right? So, and this mode, 1280 by 1024 with 24-bit addresses, it has the code 11B in hexadecimal. Well, 11B, and it shouldn't be pronounced as 11 theoretically, but yeah, so that. But yeah, you can, from this VBE info, you can get the video mode pointer. And what you can do is then you can use something called mode info, or VBE mode info. And this is the instruction 4F01. And again, DI is going to have an address, and you're also going to need the CX register, if I remember correctly. Let me just check. Yeah, that's going to be CX, and CX is going to be the mode. So what you're going to do is use the VBE info instruction in order to get the video mode pointer. Once you have the video mode pointer, that is the first mode that you can set as your CX. And using this instruction, you can put into an address, into a specific format, the information about this first mode that both the video card and display supports. And this will give you different information, such as the X resolution, the Y resolution, bits per pixel, and it will also give you the physical address of, the physical base address of frame buffer. So, well, you probably you have like a desired resolution, right? So what you can do is, once you call VBE info and you get the information about the first mode ID, you get information about this mode with this ID, and you check the X and Y resolution. And if it's okay for you, then you'll set this mode. But if it doesn't suit you, you simply increment mode by 1 and call mode info again. And if this suits you, cool, pick it as your mode. But if it doesn't, then increase CX again and such. So VBE info is very cool because it gives you the ID of the first mode that is supported by the video card and the display, and you can simply increase it in order to, by 1. You can increment it to get next mode IDs that work. Right, and you're supposed to get officially information and not append, like statically, that this ID is this mode and stuff. You dynamically have to see, using the mode info instruction, what precisely is this mode on this specific machine. And then once you've found a mode, you found that you like, and you have this mode ID that you like, you can set a mode using the instruction 4F02. And here you don't use the DI because you're not going to, you don't use the DI register because you're not storing any information. And as BX, you're going to place your mode. So that's pretty much the entire procedure. So you only here have to give addresses to like those structures where you're going to store all the different parameters, and those are easily available, easily found in the official VBE manual. So yeah, set this, call this, and you'll get at this address a bunch of info. One of them is the video mode pointer. Set the video mode pointer as CX, call this instruction, right? So AX sets this, sends this interrupt, and at the address that you've chosen in the structure, you're going to get parameters like X resolution and Y resolution, or bits per pixel. If those parameters fit you, great, choose that mode. If not, increase CX, check again. And then once you find a mode that satisfies you, set then as BX, set AX to this, call it so you call set mode. Fantastic. And once you've set a mode, obviously you're going to want to write to it, and for that you need a frame buffer address. And for the linear frame buffer, this mode info part, it's also going to give you a parameter called the physical base pointer. And this is going to be the physical base address of your frame buffer. So you can write to that directly, or like if you're setting up paging, you can set the virtual addresses such that the frame buffer is always at a consistent location. It will always have the same virtual address. You can do things like that, right? So that is generally how you handle graphics, right? And well, you're usually going to be dealing with, or you probably want to deal with, an LFB or a linear frame buffer. And let's say that you managed to get something high resolution, right? So for example, let's say that you got to the mode I previously mentioned, 1280 by 1024 with 888 format, which means that a byte for red, a byte for green, and a byte for blue. So perhaps you haven't called VBE info at all, because this actually has a standard ID of 11B. You can't entirely depend on it, but any machine that I've generally tested this mode on, it works as long as it just supports this mode at all. If it supports this mode at all, it had this ID, right? And most displays are going to support it. That's just a stupid claim that I make, but yeah. Anyway, so you get the mode info, so you set this as CX, and into this structure, which is found at this address that you set the DI, you're going to find the physical base pointer. Fantastic, you set the mode, and you have the physical address of the frame buffer, and you might have changed it whilst paging to be a different virtual one, right? You might have not done identity paging. Doesn't matter, either way you end up with some address. Let's say arbitrarily that would be, I don't know, this. It probably wouldn't be this, but let's just say that, right? And in that case, what you would do is this byte, you would set it to the red value, then the next one would be the green value, and the very next one would be the blue value. And congrats, you have constructed 1 pixel out of all of this. And then again, the next byte is going to contain the red value of the next pixel, and so on and so on. Now, if you want to place a pixel of a given color at a position XY, it's going to be the same as I talked about in 13H mode. You just have to remember about the extra parameter that you obtained through the mode info, which is bits per pixel. You'll probably want to divide that by 8. It should be a number divisible by 8. It is in the way, but, you know, if you have taste in your selection of modes, and you have a good algorithm, then it should be divisible by 8. I personally don't accept modes that don't use 24-bit color, so yeah, but you divide that number by 8 to get the bytes per pixel, and then you can easily modify your formula. So obviously you would have to move through, so you have your linear frame buffer base address, and you would add your Y resolution times Y times, well, bytes per pixel divided by 8, and then plus X times, well, no, this isn't the Y resolution, this is the X resolution, size of one row. X times bits per pixel times divided by 8. I mean, I think you can easily see how this formula works. It's the same, except we have to remember that one pixel is going to actually occupy 3 bytes. So yeah, this is fundamentally what graphics boils down to. So then you can obviously start working on a graphical user interface or something. This probably shouldn't be your priority, but yeah. So once you have something like that, you might start wondering about like how can you display images and things like that. And well, fundamentally, it always boils down to just parsing a given format. And you have to parse it into individual pixels that actually have to display on the screen, and for color values. There are different image formats. You, for example, have a JPEG, right, which uses something called the discrete cosine transform. It's really cool to mess around with that. The simplest one, if you want a very simple format, write a very simple parser and get some images very quickly in your operating system, you can use TGA, right? So TGA is a format very easy to parse into individual pixels that would have to be displayed on the screen. And there are a bunch of programs, really a lot, that convert PNGs and other images into TGA images, right? TGA files. So you can get some nice graphics in your operating system. Obviously, a consideration might be introducing fonts. Where, well, for the sake of simplicity, you'll probably using a bitmap font, which will just have encoded information about like each character, like what bitmap image does it actually correspond to. So like you have information about which pixel to color in or not. So that's basically a bitmap font, but you can also have vector fonts like TTF, right? And vector graphics are very interesting, so you might always want to implement them because they depend on curves and mathematical description of curves, Bezier curves and such. And for example, well, the boldness of text, how bold your text is going to be. Well, you can easily see that if you have a curve, which, you know, is this abstract mathematical object, and you want to draw it on a screen, and you want to make this curve somewhat bold, fundamentally, what you're doing is for any point, you would have to check, hey, is this close enough, according to the boldness parameter, to the mathematical curve? And so fundamentally, what this is going to be, since curves are going to be described like polynomials, this is a polynomial inequality. And you solve polynomials inequalities with roots of polynomials. So this is a beautiful motivation of roots of polynomials. I'm sorry, I just had to throw that in there because I come from a pure mathematical background. So mathematics and computer science, they always excite me, right? So, and vector graphics is pretty beautiful. All right, so that's generally graphics and video, right? And then when you actually have processes, you don't want them writing directly to the frame buffer because that would be nonsensical. You generally want every process to have its own little buffer, and then it will be placed onto a window which is handled by the operating system. But this actually is very convenient because either way you want to do something called double buffering. Even when you're just on the kernel level. Well, if you're just on the kernel level, I wouldn't consider doing graphics. I wouldn't consider caring that much about graphics, but whatever. There are much more important things in operating system development than a graphical user interface. But double buffering is this technique. Obviously, whenever you decode an image or whenever you perform some calculations or whatever, it obviously takes time. So what is going to happen is you will start placing individual pixels on the screen, but since they will be calculated in this slow way, you'll actually notice a flickering effect. So if you try to constantly update your screen with, you're writing those pixels and you're clearing the screen and you're doing things again, you'll notice that this is actually very slow and you'll see some weird flickering effect. So how can you actually prevent this flickering effect on a low level? Well, the idea is that you don't write the pixel value as soon as you have it. You realize, okay, I'm going to have to wait for the next ones. So instead, what I'm going to do is I have my screen, right, or well, generally speaking, display, and I simply have a buffer inside my RAM. And what I'm going to do is I'm going to instead only put the pixels that I calculate the values of inside my buffer. And only once the buffer is fully complete, once I have to perform no calculations, just pure copying over, right? Copying over each value from the buffer to the display, that's when I'm going to do it. So once my buffer is complete, I'm going to then copy all the values from my buffer to the actual display. And then again, the display is going to contain all those values, and I'm not going to write any new pixels onto the display. I write all the new pixels onto my buffer, onto my second buffer. And only once my second buffer is filled with all of those values again, and I have to perform no more computations, I'm going to copy over all the values to the display. And because of this solution, the display is only updated once I fully know all the pixel values already, and I just have to quickly copy them over. And this is going to prevent the flickering effect. And this technique is called double buffering. In newer video games, there's also triple buffering, where you keep two buffers that are inactive in order to do this rendering quicker, because you have to remember that you have even more computations when you have like 3D complicated graphics and architecture, right? That's going to be even more heavy. So having two buffers that are going to have this, triangle of interchanging each other, that is going to minimize the chance of flickering even further. Okay, so that's double buffering, and it makes also sense in the context of when you have a process, right? It's going to have its own buffer, and then the operating system is going to decide, what should I actually do with this buffer? Like, where should I exactly place it so that it fits in a window that I have in my sort of graphical user interface, right? In my windowing system or my desktop environment. So the rest of the video tasks aren't that related to the operating system itself, so I won't be talking about that anymore. So let's go over to audio. So I'm only going to mention a very simple audio interface that is very known for making simple beeps and boops. And that is something called the PC speaker. And you communicate with the PC speaker using I/O ports. And it's generally, you first have to set a timer, and then basically what the PC speaker does is it simply tries to, it's a very simple device that, has little metal legs which are going to move at a given frequency. And once you turn on the PC speaker, they're going to, according to the timer, simply clutch against each other, which is going to make a sound. And we're going to do this at a given frequency, which is going to produce a sound at a given frequency. So we simply have to set the timer and then instruct the PC speaker to actually, hit those metal things against each other according to the timer. So first we're going to set the timer to a given frequency. And we do this using 2 ports. Our command port is going to be hexadecimal 43, and then our data port is going to be hexadecimal 42. And the set frequency command is hexadecimal B6. So we first send B6 to the command port. And then to the data port, we have to dictate the frequency. But the frequency is not given in anything simple like hertz. It's actually a frequency relative to the programmable interval timer. And because of this, you have this magic number of the default frequency of the PAT, which is going to be 1193,180. So you actually have to give the ratio of this over your desired frequency in hertz. And this is like what you have to give to the data port. And you need this value as by the way, you send this thing as a byte, right? And those ports only receive bytes, right? So you have to use outbeat. But yeah, this value, you need it stored as a 16-bit unsigned integer. And once you have stored this value, this number divided by your desired frequency, as a 16-bit unsigned integer, you want to first send the lower half, and then you send the higher half. So first you send the last 8 bits, and then the first 8 bits. So obviously you're going to send the lower bits with a mask, right? You simply perform an AND gate with 0f, which is going to grant you the lower byte, and then if it comes to the higher byte, you would have to mask it with F0, and then you would have to shift it 8 bits to the right. So, right, you send this to this port, and then you send the lower half of this to this port, and then the higher part of this to this port. And this should have set the timer frequency. And once you're done setting the timer frequency, you can actually instruct the PC speaker to start playing sound. And you do this through the port hexadecimal 61. So this is the actual PC speaker. And it's a relatively weird mechanism, but the way that you're supposed to make it play sound is by first obtaining a byte from this port. So we obtain a byte from this port, and then you OR it with the number 3. So that is going to make the last 2 bits equal to 1. And then you send back the byte that was ORed with 3. Right? So you get a byte, you OR it with the number 3, such that the last 2 bits are set to 1, and then you send it back to this port, and that's how you make it play sound. So those last 2 bits that's basically what they are responsible for, right? For making the PC speaker play the sound. So if you want to mute it, it is a similar mechanism, except you want to AND it with the hexadecimal number FC. And it makes sense because that's going to disable the last 2 bits back into 0. So you get the value you want to set the last 2 bits to 1 and then send it back to play sound, or you want to receive the value, set the last 2 bits to 0 and then send this back to mute the sound, and it's going to play the sound according to the frequency. And while this is playing, you're free to change the frequency at any point so that it plays a different sound at a different frequency. Awesome! You can even parse some wave files, you can see the frequencies that are there, and play some basic melodies on the PC speaker. Just remember that the PC speaker can only play one sound of one given frequency at a given time. So it really had one audio channel. So there was some technology needed in order to have a higher amount of those channels, and that's how the Sound Blaster 16, a very popular audio interface, came to be. The Sound Blaster 16 is a bit more complicated, and you also have to handle its interrupt requests and such, but it actually allows for having multiple channels at once. Or maybe what I'll do is I'll actually start writing, because I want to give a sort of perspective for audio and how it evolved. So you have a PC speaker, very simple device. You really only had like one way that it could, produce sound, and it could only produce it on one channel. The Sound Blaster 16 introduced multiple audio channels, which played sounds resembling different, let's say, instruments, quote unquote. This was pretty revolutionary, and then you would actually instruct it at which frequencies and which channel it would play different things. And the cool thing is, a lot of modern audio extension cards can still emulates the Sound Blaster 16. So if you write a driver for it and you write something like a wave interpreter so that it can play wave files, for the Sound Blaster 16 it might actually work on a modern machine. But if you want to be even more sure, then you would want to deal with the AC97. I have no idea where the apostrophe is. Whatever. Let's just put it like that. The AC97, or the Audio Codec 97, generalized this notion of channels by taking ideas that were widely used and related to some things like the discrete Fourier transform, and it simply has waves, a lot of collections of points that represent the actual movements of particles in the air. And because of that, you're not limited to this idea of channel, and you can produce a wider variety of waves and you can play them. So, AC97 already to me is pretty advanced, pretty cool, and can play a bunch of relatively high quality sound. Like with the Sound Blaster 16, you still are limited to a couple, like let's say quote unquote instruments. You can easily see that something is done with Sound Blaster 16. AC97, in my opinion, relatively like high quality audio in the sense that you already have audio. You have audio recordings, and you're really comprehensible and stuff because of a way that it generalized audio. But if you want something even more advanced, even more fancier sounding, you always have IHDA, which is Intel High Definition Audio. I've never implemented this one. If someone does, watching this video, feel free to, I don't know, hit me up and share your experience with implementing the Intel High Definition audio interface. So that's video and audio, which pretty much covers the most important output devices that you would generally deal with on a computer. So now I want to talk a bit superficially, just to give an idea of how one could evolve their operating system further by adding support for more I/O devices. Obviously, the obvious thing that comes to mind is getting USB support, because, I mean, come on, USB is the most ubiquitous support anyways. Most of my devices that are currently connected to my computer, the camera that I'm using to record this video, my mouse, my microphone, they're all connected for USB. So USB really is as universal as the name suggests, because USB obviously stands for Universal Serial Bus. And the Universal Serial Bus is the fundamental idea of it is you have a USB controller, right? There are four main ones, which would be the UHCI, which is like the Unified Host Controller Interface. OHCI, the Open Host Controller Interface, EHCI, Enhanced Host Controller Interface, and the newest one is like XHCI, or the Extensible Host Controller Interface. So UHCI and OHCI were like the first ones. They supported like USB 1.0, slow transfers. Then when faster transfers came by with the standard called high speed, they decided that a new host controller interface standard is necessary for that, and that's how EHCI came to be. And EHCI is probably my favorite USB controller. And then there was also this another USB standard called Super Speed, which introduced mechanisms like the doorbell for handling high-speed packets. And that's how the Extensible Host Controller Interface, or XHCI, came to be. And what you have to do is identify one of those controllers, start communicating with it, and then you can use it in order to enumerate USB devices that are connected to it. Because, USB assumes a sort of tree model, where you always have something called the root hub. And to the USB controller, you're going to have a bunch of USB devices connected. And you'll actually, since it's a serial bus, you'll actually have to have job queues and things like that. And this tree structure and tree algorithms can help with that. But yeah, so you have a root hub and you have different USB devices. One of them may be a hub, which is going to have even more USB devices, right? So you have this tree-like structure that USB assumes, and basically you can use one of the controllers in order to, as I said, enumerate the devices and you will find, so you have to write basically a way to handle one of the USB controllers, and use it to enumerate devices, and then to get info about specific devices that you want, such as HID devices, which are human interface devices, like a mouse or a keyboard. And you write an abstraction layer, and then you're able to get different sorts of information about that so that it can later communicate with those devices. So USB is generally abstracted away. Like, for example, like you usually won't get direct information like that this is a mouse. You'll get information that this is a pointing device, and you might, for example, get information that it is an absolute, well, a relative pointing device, right? Because you have relative and absolute pointing devices. So an absolute would be like a graphics tablet, where at any point, if you place it over any point of a graphics tablet, it's going to move the cursor to that point corresponding to it on the screen. So that's an absolute pointing device. But you also have like relative pointing devices, like a mouse, where you instead look at the changes in movement of the mouse. So like if I take my mouse and move it to a different point, nothing's going to happen on the screen. Things only happen when I physically move a mouse a given amount, and that's the amount that the cursor is going to move on my screen. Yeah, so USB support is something one might consider. There are also some interesting technologies and ways that information can be sent, such as isochronous transfer, right? So this is used mostly in AV devices like I'm currently, and I know this because I've changed it in the settings, I'm using isochronous transfer for my camera or for my microphone. So the idea of isochronous transfer, and you can probably easily see why that would be useful for devices like AV, is that you dictate. Well, first, a process is done called negotiation. And this isn't only related to isochronous transfers. This happens on any audio-visual device, but it will give some context for why you might want isochronous transfer. So negotiation is this process that happens with devices such as cameras, where the operating system and the camera interchange information about all the different parameters. So for example, you might have the camera resolution, and what happens is the operating system proposes some resolution. And then, through the USB interface, a device like the camera gives a resolution back. And then, well, there will probably be a mismatch, those resolutions won't match. But there is this desired resolution that the operating system wants, right? But what the operating system sees is, okay, I want like full HD, but I see that this isn't entirely possible. The camera has suggested something that is way, way lower. I will lower this a little bit. And the camera sees that, okay, the operating system definitely wants a resolution that is way higher, so I'm going to increase it. And this cycle continues according to an algorithm, and eventually there will be a point where they're either equal to each other. Well, there will be a point at which they will be basically equal to each other. And that is the end of the negotiation. This whole process is called negotiation. And this sets certain parameters. And then isochronous transfer is all about basically sending and generating electric signals, or for example, communicating through USB at given equal intervals. And this is good for devices such as audiovisual devices because it provides a given deadline. A deadline for when a USB packet should actually arrive. And this is very convenient because whenever you lose, because the sort of part you might not want to like about deadlines is if by a deadline an operating system does not handle a given packet, then it will be entirely lost. But this is actually good for something like a camera, because if I lose a pixel or two, I don't actually care about that. Or for a microphone, if it doesn't catch all the different vibrations in the air that make up a sound that I made, I also don't care about that. Which is why isochronous transfer is good for devices like that. And also, the process of negotiation was important, because now the negotiation dictates how, what intervals should this be sent, and how much, fault tolerance is expected and such. So yeah, you have a lot of very interesting solutions if it comes to the universal serial bus, and I would highly recommend, taking a look at the documentation, well, later on if you want to, evolve like the input-output stack of your operating system. You can take a look at the documentation of one of those controllers. You can see how you can communicate with this controller through a bus like PCI or PCIe usually nowadays, in order to get information from it, and then how to use that information in order to enumerate devices, and how using the info about the devices you enumerated to get info about a specific device that you can use to then communicate with that device according to its documentation. Right, so that was a very, very superficial, obviously, overview of the universal serial bus. So, in order to conclude this topic of input and output devices and operating systems, okay, just before that, storage devices. So storage devices obviously exist. So if it comes to USB, you also have storage devices, and they use also like special methods of transfer, such as bulk and like bulk. I, to be honest, have never fully implemented a USB-based storage device. Usually I have used simply like ATA IDE, right? So you have advanced technology attachment is, like you probably recognize when you have like ATA drives, and then you have like SATA drives. And there's this, nowadays ATA is also called PATA, because this is advanced technology attachment, and then there was this, and this was originally parallel. You might actually remember this. You had like those huge sort of like tapes that would usually be white, and you would have to connect them to one end of the hard drive, and then your controller, right? Your ATA controller. And it would be this huge parallel bus that would make access to other components on the motherboard very difficult. So you had that, and nowadays that is usually called PATA, because it used to be parallel advanced technology attachment disks. Currently you have a serial version, or SATA, and I've seen many people also implement NVMe, non-volatile memory, probably not extended, right? Enhanced, extended, perhaps extended. They always add those things at the end, but non-volatile memory. Yeah, I've never implemented this one myself. I've seen a lot of people do it. It seems pretty cool. I've messed with ATA and SATA. I usually prefer ATA for just its simplicity. Again, I don't think I'm going to explain precisely how you write data to an ATA drive, because I consider it to be relatively tedious and trivial to explain, but you can easily check the documentation. And it is really just, it's a couple bits of communication they use in order to write to an ATA drive. Or read from an ATA drive, for that matter. Writing and reading pure data from a mass storage device like an ATA IDE drive is not that difficult, but then you get into some, well, perhaps not difficult things, but at least a bit more interesting from a theoretical perspective, when you have to deal with file systems. because file systems are fundamentally this way of actually organizing this data on a disk. Because sure, you can have pure ones and zeros and can write those bytes and you can read those bytes, but it would be cool if we could interpret this in some useful way and see collections of data that are related to each other. And those related pieces of data is what we're going to call a file. But that's going to be in a separate video about file systems. Okay. So, let's summarize what an operating system does generally in order to deal with input and output devices. So, first of all, it has to initialize the peripheral devices. There has to be an initialization of, I'll just say, devices and cards, right? Because you might also deal with extension cards. You might have to, turn on the second PS2 port and do things like that. Once you're done with that, you'll continue on with the enumeration of buses. And, obviously this will be sort of connected to each other. But yeah, so the enumeration of buses, you have different buses to which the extension cards and the devices are going to be connected to. So you're going to have the universal serial bus, peripheral component interconnect, peripheral component interconnect express. Oh yeah, that's what VE stood for in VE and VBE, non-volatile memory express. But yeah, so you have the enumeration of buses. You want to see from all the buses on your computing system, what are the different devices that I actually have, right? And what are the extension cards that I have to deal with? So you're going to have the enumeration of buses, and then you have resource allocation, because, well, obviously, those devices, those extension cards, they're going to use different resources such as IRQ channels, right? You have different devices and those different IRQ channels, right? And you might go into some conflicts, right? Or, for example, DMA channels, right? That are direct memory access. So you'll have to deal with allocating those resources to the devices and the extension cards. So back in the day, a person had to manually configure this in the BIOS. So a person would go into the BIOS, and they would have to configure all the different IRQs and all the different DMA channels such that there are no conflicts. If they messed up, then everything would be messed up and it wouldn't work because you would get conflict of interrupts and such, and the operating system would not handle that correctly. So back in the day, you'd have to do this manually. Nowadays, you have a mechanism called PNP, or plug and play, where the device actually provides information. It's like, hey, those are the IRQ channels that I use and everything, and it's very easy not to get into conflicts. And in fact, devices are so well designed nowadays that even if you don't pay attention to PNP, as long as your operating system is small, you usually don't even have to worry about it, and you probably won't get into that many conflicts. But in the long term, you might consider about implementing PNP and knowing, getting all the information about the RQs and everything, and ensuring that there are no conflicts, because you're going to get information about RQs anyways to use the device, right? But in the part of ensuring no conflicts and actually allocating resources properly. Okay, and yeah, and then you have driver matching. So we have initialized everything, we've initialized all the buses, communicate initially with the buses and everything, and then we've enumerated them, seen all the devices and the extension cards. We've seen what sort of resources they need and ensure that there are no conflicts. And once we have that, we have to match the drivers to all the different devices and extension cards we have. So for example, let's say we have, we initialize PCIe and we initialize a network, and the network card initializes itself and things, right? And we enumerate the PCI bus. We see, okay, there's a network card, right? The network card fires on this RQ channels and needs this DMA channel. And then you match the driver. Okay, let's see. We've gained information about the network card, and we know, for example, that it is a PCNet2, right? Oh, okay, the operating system has a driver for PCNet2. We've written one. Okay, we're going to handle this device on these RQ channels and such. We're going to handle the interrupts and everything according to the driver for the PCNet2 network card. And you do that for everything. So, a PS2 mouse will do this and this. You match a driver. We've written a driver for a PS2 mouse. And this is how input and output devices are handled in operating systems. So, yeah, that's probably everything I wanted to say in this video. And now we're going to get into a couple more interesting things related to operating system development. As probably many of the viewers have noticed, I definitely have way less time to work on this series. But I've decided that in the first half of the year, I want to produce enough videos to say that I have completed in the series, in the sense that if I want to add anything, it would be appendices, right? Because I want to stick to my original goal of creating an operating system that would fit that initial definition. And I made that goal so that I can definitely manage to actually do it, and so that I don't make any unrealistic expectations. So, thank you very much for watching the video, and I hope that we'll see each other in the next one. The next one will be very cool. It will be about memory, a very nice resource in operating systems.